Hello, I'm Dr. Michael Ayomo, a senior lecturer with the Department of Industrial and Systems Engineering, University of Pretoria, South Africa. I am a multidisciplinary researcher operating with a background in both technical and management process systems engineering. My primary research domains spread across manufacturing systems, management systems, artificial intelligence systems, and complex systems. In this presentation, I will limit my discussions to precision computing in manufacturing systems. This speaks to the title of discourse, christened Precision in Manufacturing Systems Computing, a Case of Surface Roughness Prediction. Surface finish is a high-precision machining task. The literature over the years have shown that for metallic materials, the higher the surface roughness, the higher the levels of wear and corrosion. Also, the level of thermal and electrical conductivity get lower with higher surface roughness. Both semiconductors and metallic materials used in electronic devices, including computers, smartphones, appliances, medical equipment, aircraft, etc., can be negatively impacted by a poor surface finish. Surface roughness is a good predictor of mechanical parts performance. In most engineering applications, the quality parameters for surfaces and parts are quite tight for the purpose of product reliability. A hybrid scheme of difference analysis with feedback control premised on the use of dynamic weights produced an accurate output in comparison with some competitive techniques in the literature. The novelty of the proposed hybrid model lies in its ability to predict and recover existing datasets with an error margin approximately zero. This predictive efficacy is premised on the use of set points and transient dynamic weights with a forcing function for feedback iterations. 3 experimental levels and factors were considered in the current presentation here, hence resulting in 27 possible outcomes. The simulation trial, anchored on MATLAB software, was divided into 2 subcategories, namely prediction of surface roughness for cutting combinations with vector points off the edges of a mesh diagram referred to as off-edge cutting combinations, and the recovery of other cutting combinations referred to as on-edge cutting combinations. The schematic diagram of a machining experimental setup is as presented on this slide, covering the high precision lathe machine and the peripherals such as a PC, a dynamometer for force measurement, and a signal amplifier. Normally, after a machining operation is finalized, a surface roughness measurement is often carried out with the use of a texture testing device with units usually in micro or nanometers. It is only after this that the need for a predictive model comes to play. A predictive model developed to recover the measured surface roughness reading is as presented here. The need to utilize highly accurate mathematical models in the recovery of experimental readings is quite significant if the outputs of future machining parameters are to be explored theoretically. It is far less cheap to conduct computer simulations in a bid to understand the surface finish behavior of planned unexperimented machining parameters rather than go to the lab to repeat chains of experiments that would turn out to be a waste at the end. This slide presents a generalized, compact computer adaptable algorithm as deployed in the research. The mesh diagram utilized in the difference analysis modeling is presented herein in the compact and open views. The three cardinal coordinates x, y, and z depicted as A, B, and C were utilized to represent the three machining variables. These variables include the cutting speed, the feed rate, and the flow rate. The table presented herein contains data for a particular machining experiment with 3 levels and 3 factors. The table presented herein contains the 27 experimental outcomes imagined from 3 levels and 3 factors design of experiment. This slide presents the feedback loop that connects the experimental outputs to the difference analysis algorithm. It further elucidates the process of adaptive weight generation for accuracy enhancement of surface roughness prediction related to the off-edge cutting combination points, that is, points that are off the edges or vertices of the mesh diagram presented earlier. By default, each of the off-edge cutting combinations are iterated until the actual response captured by the estimator is greater than or equal to the desired or experimental surface roughness reading. At the point of stability, a zero output response takes place at the comparator level. The discrepancy between the predicted surface roughness and the desired readings serves as a driving mechanism for the operation of the adaptive weight algorithm prior to attainment of a steady state condition by the off-edge cutting combination points. This action of the adaptive weights is often characterized by weight gains or losses. The pseudocode in here presents the workings and activities of the feedback loop. The same pseudocode continues on this slide, showing how the dynamic weights are computed. This slide presents both the transient and steady-state dynamic weights and predicted surface roughness readings for all 7 points depicted as off-edge cutting combinations. Iteration 1, as presented in here, is absolutely transient behaved. This can be seen across board all 7 off-edge cutting combination points. A steady state condition for machining parameter A2, B3, C2 was attained in iteration 2. However, the dynamic weight adjustment continued up until the 5th iteration without changing the surface roughness reading. This is premised on the fact that the predictive models are tightly coupled. Hence, the generated weights are affected by the transient behavior of other cutting combinations within the connected system of models. A steady-state condition for machining parameters A2, B2, C3 was attained at the end of the third iteration. However, as in the previous case, the weight remained transient until the fifth iteration. Furthermore, iterations 4 and 5 attained a state of stability for surface roughness prediction of cutting combinations A1, B2, C2, A2, B1, C2, A2, B2, C2, and A3, B2, C2, all depicting specific parameter combinations as earlier presented. Machining combination A2, B2, C1 only attained a steady state condition at the end of the seventh iteration. The eighth and ninth iterations showed stability attainment in both weight variation and surface roughness prediction. A comprehensive table detailing the machining parameters, experimental surface roughness readings, and percentage discrepancies of the predicted results relative to the experiments are presented in this table. This slide presents a comparison of the outputs between the experimental and the abductive network algorithm. This slide presents a comparison between the outputs from experimentation and the regression analysis model. Furthermore, this slide presents a comparison between the proposed hybrid model and the experimental results. The abductive network had a reduced graphical discrepancy between the predicted and experimented in comparison with the regression analysis technique, while the proposed approach of difference analysis and dynamic feedback scheme presents an absolute trend match between the computational and experimental outputs. Additional comparative experimental readings are presented herein between an artificial neural network predictive model and the proposed model. Also contained in this table are the percentage error of the artificial neural network technique and predictive outputs of the proposed technique in relation to the experimental output. The proposed approach recorded a zero error discrepancy between the experimental and predicted results through an absolute trend match with the experimental outputs. In here, we can see the iterative dynamic weights and surface roughness prediction outcome. Unlike in the previous predictive exercise, the convergence herein was faster due to increased values for initial weights assignment. The predictive iterations for all 7 points referred to as the off-edge cutting combination were characterized with random selection of initialized weights within the range of 1.2 and 1.5, as numbers within this range facilitated convergence of all the 7 iterations. A steady state condition was attained herein for all predictive machining combinations at the end of the second iteration. A graphical plot comparing outputs from the use of the artificial neural network technique and the experimental output was carried out as displayed here. The graphical mismatch or discrepancies is a clear indication of the errors associated with the artificial neural network technique. Furthermore, a graphical plot comparing outputs from the proposed technique and the experimental output is as presented here. The strong correlation between the two graphs is an indication of the high level of predictive effectiveness of the proposed technique. Generalized algorithms adaptable to computer coding in a bid to expand the design of experiments to include more levels and factors is presented on this slide. This ranges from 2 factors n levels and 3 factors n levels to some relatively high values. With this, more predictions can be carried out for new combination of machine parameters. As presented, the generalized algorithms continues on this slide. In conclusion, an optimum computational model for surface roughness prediction in a shop floor for machining operation has been presented. The developed predictive model premised on Gauss-Seidel difference analysis approach and an adaptive feedback scheme anchored on the use of dynamic weights resulted in a zero error margin between the measured and predicted surface roughness readings. The developed model would aid with a near to perfect results for surface roughness readings of future machining parameter combination. Thank you.